In this particular question, we've been told that we have a cylindrical container that is open at the top and that it's designed to hold 200 milliliters of liquid. We must determine the dimensions of the container if the surface area of the container must be a minimum. You could actually see a practical application for this type of question as a company who is trying to package a certain product is trying to minimize the use of materials for the container for that particular product. Well, we start by drawing ourselves our cylinder, and we should recognize that we're dealing with two particular concepts simultaneously, volume as well as area, surface area that is. We know that volume for a cylinder is V equals pi r squared h. In this case, the volume is fixed at 200 milliliters. So we can state that 200 is equal to pi r squared h. Now we need the equation for the surface area. Now our surface area in this case is going to be made up of the cylindrical shell as well as the circle that is the bottom of the container. There is no circle on the top of the container because they tell us that it's open at the top. So our surface area formula is going to be A equals 2 pi r h, that's for the cylindrical shell, plus pi r squared, that's the surface area of the circular bottom. Now when you take a look at that equation, you'll note that we are dealing with three variables, a, r, and h. So this isn't a function. What we'd like to do is make it into a function. So what we can do is return back to our volume equation, 200 equals pi r squared h, and we can rearrange that equation and solve for h in terms of r. So h is going to be equal to 200 divided by pi r squared. I can now take this expression for h and substitute it into our surface area formula. So surface area, A, is going to be equal to 2 pi r times 200 divided by pi r squared, and then that's added to that is pi r squared. Well, now I'm just going to simplify that expression. I notice that we have some division that can occur. Pi divided by pi is 1, and you notice that we have an r in the numerator and an r squared in the denominator. So when I do that division, I end up with my surface area, A, is equal to 400 divided by r, and then we add to that pi r squared. I'm just going to express this in a slightly different form. A is going to be equal to 400 times r to the negative 1 plus pi r squared. Now what I'd like to do is take the derivative of this function and set this derivative equal to 0 so I can find the minimum in this case. So a prime is going to be equal to negative 400 r to the negative 2 plus 2 pi r. I set that derivative equal to 0, and instead of stating negative 400 times r to the negative 2, I can express it as negative 400 divided by r squared, and I add to that my 2 pi r. Now when you take a look at that equation, it's a little more challenging to solve because we have an r squared in the denominator. What we can do is multiply everything on both sides of the equation by r squared. So we end up with 0 equals negative 400 plus 2 pi r cubed. Now we can simply rearrange and solve for r. First we add 400 to both sides of the equation, and then we divide both sides of the equation by 2 pi, so we end up with r cubed is equal to 400 divided by 2 pi, and then it is just a simple matter of taking the cube root of that value, or raising it to the 1/3, and we find that r is approximately equal to 4. So we now have our radius. We need to find the height of our cylinder. Well, we know that height is equal to 200 divided by pi r squared. That came from our volume equation. So h is going to equal 200 divided by pi times 4 squared. And when I solve for that, I end up with h approximately equal to 4. Now the only thing I have to check for is, am I indeed dealing with a minimum? So I need to look at my second derivative. A double prime is going to be equal to 800 r to the negative 3 plus 2 pi. I now simply substitute in that value of r that I worked out, which was 4, and I find that a double prime is equal to 18.8 when r is equal to 4. What we'll note here is that a double prime is greater than 0. Since my second derivative is a positive, I can clearly state that we are dealing with a minimum. So the dimensions of this cylinder that would minimize the surface area and still have a volume of 200 milliliters would be a radius of 4 centimeters and a height of 4 centimeters.